Space is filled with gates to infinity. Beams of light traveling among the stars, the movement of galaxies, and the mysteries of dark voids all are intricate parts of the universe. However, behind these immense spectacles lies a great power. In the depths of space, the force of attraction between objects is one of the most fundamental interactions of the universe. In this documentary, we embark on a journey to understand this universal phenomenon. In the infinite voids of space, gravity brings stars together, keeps planets in orbit, and holds galaxies together. Sir Isaac Newton's universal law of gravitation presents a simple and understandable formulation of this force. However, in the early 20th century, Albert Einstein made a discovery that completely changed our understanding of the universe, revealing how gravity and spacetime are intertwined. Einstein's general theory of relativity explains how gravity interacts with spacetime. An object bends the fabric of spacetime, causing other objects around it to be drawn towards it. This curvature, like a projection, affects everything traveling through space. In this documentary, we will explore the fundamental concepts of gravity and build the necessary foundation to understand this mysterious force in the depths of space. To comprehend this immense power behind the gates to infinity, we will witness the extraordinary impact of gravity throughout the universe. Gravity is defined as the force of attraction between existing objects in the universe. This concept influences a wide range of fields from astronomy to everyday life and constitutes one of the fundamental forces of the universe. Understanding the structure of the universe, grasping the concept of gravity is crucial. Gravity determines the gravitational pull of one object's mass on other objects. Isaac Newton's universal law of gravitation provides a fundamental tool for calculating the force of gravity based on the masses of objects and the distances between them. This law is used to explain the movements of celestial bodies, planetary orbits, and other astronomical events. Gravity appears not only in astronomy but also in our daily lives. The reason an apple falls to the ground is the gravitational force created by the Earth's mass. Similarly, the ascent and descent of a ball in the air can be explained by the concept of gravity. Gravity keeps planets in their orbits and regulates their movements around the Sun within the solar system. It brings stars together between galaxies and shapes galactic structures. Additionally, it plays a critical role in understanding the most mysterious phenomena of the universe, such as the formation and evolution of black holes. Isaac Newton's universal law of gravitation is one of the cornerstones of modern physics and has greatly contributed to our understanding of how the universe works. British physicist and mathematician Isaac Newton formulated the law of universal gravitation in the late 17th century to explain the motion of the universe and the orbits of planets. This law states that all matter attracts each other, and the gravitational force is a function of masses and the distance between them. Newton's universal law of gravitation is as follows: the gravitational force between two masses is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. This law is used to explain the movements of planets around the Sun, the Moon's orbit around the Earth, and many other observations related to celestial bodies. For example, there are essentially the same principles between the fall of an apple to the Earth's surface and the orbit of a planet under the influence of the Sun's gravitational force. The universal law of gravitation fundamentally expresses the concept that masses attract each other, and this gravitational force is determined by mass and distance. This law is used in solving many physics and astronomy problems and forms the basis of modern astrophysics and mechanical sciences. Newton's discovery accelerated the scientific revolution and deepened our understanding of the universe's workings. The law of universal gravitation is a significant example of his scientific genius and discoveries. Albert Einstein's theory of general relativity, on the other hand, is one of the most important scientific discoveries of the 20th century. It fundamentally changed our understanding of the universe's structure and the basic principles related to gravity. General relativity was developed by Albert Einstein in 1915. This theory suggests that gravity curves space and time and that this curvature determines the motion of objects. General relativity provides a fundamental framework used to explain the large-scale structure of the universe and cosmological phenomena. Einstein's theory of general relativity explains the mechanism underlying gravity as follows: mass bends and curves the fabric of space and time, causing other objects to follow paths in this curved spacetime. The gravitational force of an object creates a curvature in the surrounding spacetime, which affects the motion of other objects. This curvature determines the trajectories of objects. Spacetime can be thought of as a kind of fabric. A massive object, such as a planet or a star, bends this fabric. Mass creates a depression in spacetime, and other objects move along trajectories that follow the curvature around this depression. This is analogous to a ball falling into and moving along a circular orbit within a depression. According to Einstein's theory of general relativity, gravity is actually a consequence of the curvature of spacetime. Objects move freely within the curvature of spacetime, but this curvature determines their motion trajectories. Therefore, the attraction of one object to another is simply a consequence of the geometry of spacetime between these objects. The theory of general relativity is significantly different from Isaac Newton's law of universal gravitation. Newton's law describes direct gravitational interaction between masses and does not use the concept of spacetime to explain gravitational force. Einstein's theory of general relativity, on the other hand, explains gravity as the curvature of spacetime, and this curvature determines the observed gravitational effect between objects. The theory of general relativity provides a deeper understanding of gravity and is used to explain many observed phenomena. For instance, general relativity plays a significant role in explaining cosmological phenomena such as the rotation of galaxies, the existence of black holes, and the expansion of the universe. Additionally, general relativity predicts the existence of important physical phenomena like gravitational waves. Einstein's theory of general relativity is considered a revolutionary discovery in modern physics and cosmology, and it remains an active area of research today, garnering significant interest. The expansion of the universe and gravity are two fundamental topics in cosmology and are closely related to each other. Understanding the structure and functioning of the universe is important for comprehending these concepts. The expansion of the universe is a significant phenomenon discovered through observations and cosmological theories. According to the Big Bang Theory, the universe began expanding from a very hot and dense point. This expansion continues, and it appears that every point in the universe is moving away from each other. The relationship between the expansion of the universe and gravity is better understood through the theory of general relativity. A massive object bends the fabric of spacetime, creating a depression around it. Other objects move along the curvature of this depression. The expansion of the universe is also based on the theory of general relativity. As the universe expands, spacetime itself expands, and the expansion of the universe affects the structure of spacetime. In this context, as the universe expands and spacetime expands, gravity also plays a role in this expansion. Along with the expansion of the universe, the curvature of spacetime between objects can also change. Thus, the expansion of the universe and gravity are important concepts that need to be considered together to understand the structure and evolution of the universe. Gravity is a fundamental force in the formation of galaxies and plays a crucial role in shaping the observed structures of galaxies in the universe. Galaxies consist of various components such as stars, gas, dust, and dark matter. Gravity is a key factor in bringing these components together to form galaxies. In the early stages of the universe, small density fluctuations at cosmic scales grow and come together due to the gravitational effect. These density fluctuations grow under the influence of gravity at a certain scale, attracting more matter through gravitational force. This process leads to the collapse and condensation of gas and dust clouds, giving rise to larger structures such as galaxies and galaxy clusters. Dark matter also plays a significant role in the formation of galaxies. Dark matter does not interact with regular matter, but through gravity, it attracts and gathers regular matter. Dark matter, found in the outer regions of galaxies and around galaxy clusters, orbits the cores of galaxies, reinforcing their gravitational pull. This affects the aggregation of galaxies on a larger scale and the formation of galaxy clusters. Gravity also guides the interactions and mergers between galaxies. In the evolution of large-scale structures, galaxies can come together to form larger galaxy clusters or merge to create larger galaxies. These processes illustrate the influence of gravity on galaxy formation. The discovery of gravitational waves marks a significant milestone in the history of science and is considered one of the most important scientific achievements of the 20th century. Gravitational waves are based on Albert Einstein's theory of general relativity, developed in 1915, which predicts that gravity curves the fabric of spacetime. The discovery of gravitational waves occurred in the late 1970s and early 1980s as a result of various scientists' efforts. However, the development of technology and the availability of sensitive measurement devices were necessary for the direct observation of these waves. Large-scale ground-based gravitational wave detectors like LIGO were equipped with the technological infrastructure capable of making sensitive measurements to directly detect gravitational waves. LIGO, composed of kilometers-long laser interferometers located in Louisiana and Washington states, can detect small changes in spacetime during the passage of gravitational waves. The first discovery of gravitational waves took place on September 14, 2015, by LIGO. This date marks the first direct observation of gravitational waves resulting from the merger of two black holes. This event occurred as a result of the detection of gravitational waves produced during the collision of two black holes by the LIGO detectors. This discovery reaffirmed Einstein's theory of general relativity, and the direct observation of gravitational waves became a turning point in modern astrophysics and cosmology. Gravity and the unification of quantum physics have long been important goals for physicists. However, due to theoretical inconsistencies and challenges between these two fields, this unification has not yet been fully achieved. Quantum physics describes the behavior of the microcosm, including subatomic particles and fields, and has been quite successful. However, the theory of general relativity explains how gravity curves spacetime and describes large-scale universal phenomena. Quantum physics and general relativity are theories that are valid at different scales and under different conditions. Physicists have developed various theories to create a coherent framework between quantum physics and general relativity. One such theory, like loop quantum theory, attempts to reconcile quantum mechanics and general relativity. Another approach, like string theory, aims to unify fundamental particles and gravity within a single mathematical framework. Loop quantum theory proposes a cosmological model suggesting that the universe exists in an infinite loop. According to this theory, the universe continually expands, then contracts, and eventually expands again, initiating a new cycle. Each cycle contains conditions similar to the previous one and demonstrates a continuity where fundamental physical laws remain unchanged. The fundamental basis of loop quantum theory is the idea that the universe exists in an infinite loop without a beginning or end. This model offers an alternative explanation to the classical Big Bang theory and provides a more comprehensive perspective on the existence of the universe. It assumes that spacetime expands and contracts in an infinite loop. This theory attempts to reconcile general relativity with quantum mechanics and is used to explain how the universe behaves at its smallest scales. String theory, on the other hand, is a theory used to explain fundamental particles and the carriers of forces. It is also a potential candidate for explaining quantum gravity. At the smallest scales of the universe, particles' movements are considered as strings, and this theory attempts to explain quantum gravity in a manner that is compatible with general relativity. Adult gravitational theory utilizes the concept of quantum entropy to offer a unified explanation of spacetime and gravity. It suggests that gravity is a consequence of the totality of many microscopic particles and claims that the theory of general relativity is only valid at the macroscopic level. Experimental validation of quantum gravitational theories is challenging because such events typically occur at microscopic scales or at very high energy levels. Current technology is not sufficiently sensitive to directly measure the effects of quantum gravity. The resolution of the quantum gravitational problem is one of the greatest challenges in modern physics and cosmology. Progress in this area may lead to the emergence of a new physics paradigm and a deeper understanding of the universe. Gravitational radiation is a type of non-electromagnetic radiation that occurs as a result of the acceleration of massive objects such as black holes or neutron stars, or due to accelerating effects such as changing mass. This radiation is predicted by the theory of general relativity and is based on Einstein's theory of general relativity. The acceleration of massive objects in spacetime or accelerating systems with changing mass emits radiation. Therefore, situations such as the rotation or collision of massive objects can generate gravitational radiation. It carries energy and momentum in spacetime and propagates at the speed of light. This property means that gravitational interactions at various points in the universe can be detected by observers rapidly moving away from each other. Gravitational radiation is often produced during the acceleration or merging of massive objects, such as black hole mergers or neutron star collisions. The direct observation of gravitational radiation has been achieved through detectors that detect gravitational waves like LIGO. These observations have confirmed the accuracy of the theory of general relativity and proven gravitational radiation to be a real phenomenon. The term gravitational force refers to the gravitational acceleration. It expresses the rate at which an object accelerates as it falls to the surface of the Earth. On the Earth's surface, it is typically expressed as 9.81 meters per second squared. Gravitational acceleration is based on Newton's law of universal gravitation, which states that the gravitational force is proportional to the mass of the object and inversely proportional to the square of the distance from the Earth's surface. As the distance from the surface increases, gravitational acceleration decreases because the distance increases. However, as one approaches the surface, gravitational acceleration increases because the object gets closer to the Earth. Gravitational acceleration plays a significant role in many calculations and experiments in physics. For instance, it is considered in scenarios such as freefall motion of objects, projectile motion, and the acceleration of elevators. Additionally, this acceleration is utilized in many engineering and physics problems and is considered a fundamental value in calculations. Gravitational acceleration can vary on different planets because it depends on the mass and size of the planet. Since the mass and radius of each planet differ, the gravitational acceleration will also vary. For example, Earth's gravitational acceleration is approximately 9.81 meters per second squared. However, these values may differ on other planets. For instance, the gravitational acceleration on Mars is lower than that on Earth, at approximately 3.7 meters per second squared. This means that an object on Mars would experience less acceleration compared to Earth. Similarly, on larger and more massive planets like Jupiter, gravitational acceleration might be higher. Conversely, on smaller and lighter planets like Mercury, gravitational acceleration is lower than that on Earth. Gravity plays a significant role in the solar system and determines the motion of planets, moons, comets, and other celestial bodies. The Sun, being the most massive object in the solar system, attracts surrounding objects and keeps them in orbit. Therefore, the movements of the planets in the solar system are directly related to the mass and position of the Sun. The gravitational force of the Sun acts as a central force that determines the orbits of planets. Gravity also influences many dynamic events in the solar system. For example, the rotations of planets in their orbits occur under the influence of gravity. The mass of large planets like Jupiter can affect the orbits of other planets and cause changes in their trajectories. Additionally, the orbits of small celestial bodies like comets and asteroids are determined by the gravitational force of the Sun. Therefore, the movements of all celestial bodies in the solar system occur under the influence of the Sun's gravity and evolve within a complex balance. For new documentaries and more scientific content, don't forget to subscribe.